Myself, Wesley Jacob, Assistant Professor, Rogani College of Engineering and Technology. In this video session, we are going to deal on the subject Engineering Materials and Metallurgy, subject code ME3392, Unit 5, Mechanical Properties and Deformable Mechanism. So first we shall see some of the mechanical properties. First one is elasticity. So elasticity is a tendency of material to temporarily deform when placed under stress and regain its original shape and size upon removal of stress. It spreads, it stretches, it alters to accommodate the strain. Example, rubber. Next mechanical property is plasticity. Plasticity is the ability of a material to be permanently deformed without fracture. Think clay putty, it retains the shape or can be reshaped into something entirely new. The next property is ductility. Ductility is a solid material's ability to deform under tensile stress. This is often characterized by the material's ability to be stressed into a wire. The next property is malleability. Malleability is a similar property, is a material's ability to deform under compressive stress. This is often characterized by the material's ability to form a thin sheet by hammering or rolling. Next property is strength. The ability of the material to withstand forces of tension, compression, and torsion. We have varieties of strength: tensile strength, compressive strength, torsional strength. Next, we shall see about the hardness. The ability of a material to resist wear, indentation, and scratching. An example of hardness test that can be carried out in the lab. Different materials are used and the depth of indentation is measured. Next property is toughness. The ability of a material to withstand blows or sudden impacts. Toughness is the ability of a material to absorb energy and plastically deform without fracturing. Material toughness is defined as the amount of energy per volume that a material can absorb before rupturing. So the below graph shows the stress strain diagram and the fracture and the two fractures, one is ductile fracture and brittle fracture. Next property is resilience. Resilience is nothing but it is the amount of energy absorbed by a material in the elastic region. The next property is brittleness. A material that is easily fractured by impact without plastic deformation is said to be brittle. Example, glass. The next property is stiffness, the ability of a material to resist bending deformation. Next property is fatigue. Fatigue is a progressive and localized structural damage that occurs when a material is subjected to repeated alternating or cyclic loading. Next one is creep. Creep is the tendency of a solid material to slowly move or continuously deform permanently under the influence of stresses and heat. So the next diagram shows the stress strain behavior. So it shows a difference between the elastic deformation and plastic deformation. So elastic deformation is reversible For small strains, stress removed and material returns to the original size. Plastic deformation is irreversible as when stress is removed, material does not return to original dimensions. Next one is mechanism of plastic deformation. When a material is stressed beyond its elastic limit, plastic or permanent deformation takes place, and it will not return to its original shape by the application of force alone. All shaping operations such as stamping, pressing, spinning, rolling, forging, drying, and extruding involve plastic deformations of metal. Various machining operations such as milling, turning, sawing, and punching also involve plastic deformation. Plastic deformation may take place by slip, twinning, or combination of slip and twinning. So this figure shows the slip mechanism of plastic deformation under the load condition. Plastic deformations in metals occur by slip mechanism. When the yield stress when the yield stress is achieved, one plane of atoms in crystal lattice glides over another. Few parallel slip planes form a block neighboring with another block. Thus, movement of the crystal planes is resulted in a series of steps forming slip bands, black lines viewed under optical microscope. Slip occurs when the shear resolved stress along the gliding plane reaches a critical value. This critical resolved shear stress is a characteristic of the material. So next we shall see the plastic deformation by twinning. Certain metals, zinc and tin, deform by a process of twinning. Differs from the normal slip mechanism where all atoms in a block move the same distance. In the deformation by twinning, atoms of each slip plane in a block move different distance, causing half of the crystal lattice to become a mirror image of another half. So difference between slip and twinning according to the atomic moment. Slip In slip, atoms move a whole number of atomic spacing. In twinning, atoms move fractional atomic spacing. Microscopic appearances. In slip, we have thin lines. In twinning, we have broad lines. And about lattice orientation in slip, no change in lattice orientation. In twinning, lattice orientation changes. Thank you.